Perfect. Yeah.
Okay. So nice to see you all. Glad to see the whole house, and we are changing the speaker today. I was very excited. Finally get to the main seat. Let me just start by sharing my screen. Okay. You can see my screen, I guess. Yeah.
Yes.
Okay. Perfect.
And by the way, the presentation is in XE data. So if you just download it as usual, you will get under lecture folder.
Yeah. All right. So as Giuseppe already mentioned, from today, the class will change to another phase of this course, which will be modeling, and I'll play part of a role into it. As you already discussed in the several courses with Giuseppe, and I heard from conversations just 20 minutes ago, you have learned a lot of tools from PK tools, GDAL facilities, and you already start, crunching your data. That's really an achievement. I want to say congratulations on that. From this time, we're going to talk a little more than just using the pre-built tools. The reason for that is sometimes in real life, the pre-built tools are not enough. Have you heard about this idiom like trying to fit a square peg in a round hole? Sometimes you have to do it. For example, just gave you something from personal real experience. Back to time when I was at Yale, I tried to mess with the Bayesian modeling. One of the big and most interesting and important part in the Bayesian analysis is to estimate this likelihood function. There are different ways to estimate this function, and there are so many packages out there. But unfortunately, none of them give you a full spectrum of all the possibilities, or they not even mention exactly how to do it. And that results in a lot of uncertainty and ambiguity of a modeling outcome, which is certainly unsatisfactory. So in the end, I had to code this whole Bayesian modeling part from scratch, which allows you to explore and look at things under the hood. So that's going to be the kind of topic I'll cover in my section. I take this for now that you have already acquired ability to use the tools. If not, there's always Giuseppe sitting in the corner. The good thing from your current build-up is we have time to get into this real modeling perspective. The reason I want to do that is trying to promote what I actually mentioned in the very beginning part of class is independent thinking. And I believe the independent thinking is the fundamental engine drives innovative solutions. And I believe innovative solutions is something too interesting to everyone. All right, so as you see, we are making a change from computation or using the tools into modeling. That's a transition, but sometimes transition may also mean a little disruption. And I will just briefly elaborate with the emphasis of my part will be more on the modeling perspective. So the coding part is not so much important anymore. I believe you can code already. If you don't, you can find tools. That's maybe with some help from Giuseppe. So I will not talk too much about tools anymore. I talk a little more about building tools. So let's begin with the first part of disruption is about myself. As many of you know, we know each other already for many classes. I jump in some lectures for Giuseppe to plug in some mathematics part. So what I really want to present myself is really a fellowship to work with you along this period, to present what I've learned and what I want to share. It's just a personal perspective. I don't expect you trust me, but I try my best to present all the derivations to convince you that they are grounded Of course, we can always argue and always debate. And I also actually welcome argument and debate. And on top of that, it's also a beneficial process. It's a self-enrichment process. People say the best way to learn is to teach. Well, I expect by the time I speak that, this sentence, there may be some disturbance in the audience. I cannot really catch you because I'm reading in front of my screen. I just want to ask those people who are already holding tomatoes or rotten eggs, just 1 second. It's not a very selfish statement. It's about self-enrichment on both sides. So I teach in this class so that I can get the benefit of re-enriching myself, and so do you. So I will also try to create opportunities in the class so that you can present your materials or in a way to teach. I will elaborate that more in the following part. So I hope you can speak up yourself. We want to build I want to build an interactive environment. It's important is how the part of I want to lead will designed to be in that way, because if you don't talk, I don't know whether you have comprehended material correctly or not, or whether I have explained myself clear or not. And also we have a little challenge with Zoom because I can only see one screen at one time. I know there are some active functions, there are also emotions, there are also chat box, but it's a little hard for me to look at those things at the same time. So please feel free to speak up if you would like to. And I will also create hours specifically in the class time that you can get in discussions. You'll find questions, activities in the slides. I will maximize the utility of class hours because I think that's very important. It's a way to measure how efficient you use time and how efficient you prepare your materials. When I was in college, one of the things I really don't like is this professor-student stop in time. So I will not do that to us, and I hope you also see the value of doing so. Another way interaction is material time. I think many of you already decided to travel. I also feel interested in. Actually, I've been there a couple of times already in the past. It's a really wonderful experience if you have never been to. But there are little complications on my side. I cannot make a promise right now, but I'll try my best. Even if I were not able to make it, I'm happy to coordinate with you through remote fashions to discuss, projects and other things. But as you see, I'm a little more mathematical oriented person, and that also help you to understand what kind of questions you may want to ask me or work with me, or how to design your project if you want to have my involvement. And all this will, I want to do some structure with the class because I think, if you want to finish in time, we have to really build each block in such a way that we know when things start, when things finish. So we have a very nice design. We start from the sharp hour. So I want to maintain that. So I hope each class will start at each sharp hour. And that's a very clear and precise statement. Each sharp hour, you count yourself how many sharp hours that's within the span of your class time. I want to try to maintain the duration of each section to be within 45 to 50 minutes. The reason for that is several reasons. Most people cannot keep attention beyond that time point, and that's statistically and neurologically studied and proved. And also, it's not very good for your health if you're staring in front of a computer screen for too long. And I cannot stay in front of staring at my computer so long, so I hope this is going to be good time for both of us. And that means if you apply the condition 1, 2, that means you will have 2 breaks during each entire class. Yeah, the last one is about lecture notes. As Giuseppe already mentioned, I will upload lecture note updated each time before the class. And there may be variations in the versions, so please take the latest one. That maybe you have the latest updates. I will put assignment and questions, of course, lecture materials, all in the package of lecture notes, so that you have only one piece in your hand. I will also respond to some questions in case you have, no matter what is something wasn't clear in the previous lecture, or there's some questions in the lecture notes you would like to work on, you want to have some input from me, anything, or even reading assignment, I'll be happy to do so. But please let me know, because if none of you have the interest in any particular questions or problems, that means is a failure in design. So I hope I will try to avoid it, but I need to know, because ultimately I'm not you. I have to estimate and do my best to estimate. As I mentioned in the very beginning of our class, I try to get everybody in as much as I can. But we always have to realize we are a very diverse group. So please help me provide feedback, provide input, so that I can know where you are and how we can shape the class together. I'll definitely consider updating materials if you want to have some particular subject you want to cover. And some of you already contact me privately, for example, species distribution modeling or some other particular subject. I'll try my best to fit in the lectures of my sections, if possible. I will promote the in-class activities. I will try to get you to talk as much as I can, so that we have an interactive mode of actions. And lastly, the Slack channel, unfortunately for me, is kind of broken. I haven't been able to recover it due to some accident. So if you want to have a question to something, please feel free to email me. I put my email address over there. I may not respond through email. Like I mentioned before, I want to put emphasis in the class times. So I will allocate time in the next lecture to address any questions that came to me. So if you have questions, I'll definitely address it, but may not be in the format of emails, but definitely in the format of conversations in the class. So that's more or less about the logistic part. I don't expect any questions at this point, but if you do, feel free to voice out. Otherwise, I'm going to move on to the modeling part of our talk. All right, so I don't hear anything. Let's go on with the subject of modeling. Before I start, can I pose a question to everyone? So what's the motivation of you practicing modeling? Or what makes you interested in modeling? Building models. Why do you want to do models? Anybody want to speak?
I can jump in.
Yeah,
you hear me? Yeah.
Yeah, here you go.
Well, for me, I'm basically a lot of my work does underwater habitat mapping, and unlike in terrestrial environment, we have very little sample size because we gotta send robot down like in the deep sea to get our occurrences. So modeling is a tool really that allow us to predict where a species can be found, and then it helps us for our sampling missions, which are, once again, they are very costly because we're using boats and stuff. So if it increases our success for our mission at sea to kind of model where the species can be, then we can just go validate these.
Yeah, great. That's a perfect example. I mean, I would say this is falls in the category that modeling can help you reduce the cost, increase the validity of your experiment design. That's definitely one valid point. And any other people want to say something? Okay, so if not, I'll talk about the motivation from my side, why I want to do modeling. What motivates me? Apparently the previous answer was one of the reasons. And the most important reason from my perspective is sometimes you have to do models. And sometimes the experimental condition is not reachable. For example, here, if you want to study the collision of two black holes, you cannot do that experiment anywhere, at least to my knowledge, and with this current technology. Then you have to do model. And this is a picture actually, we get more and more excited about this gravitational wave since its discovery in 2015. And that's another point. Actually, the prediction about existence of the gravitational waves was actually done 100 years ago. It takes 2,000 scientists, 100 years in the world collaboratively to capture and discover this phenomenon. So the modeling can also help you to make discoveries. But it's also not first time. For example, the orbit of Mercury, the precision of GPS system and our time corrections, all this happened in the past, and all due to the merit from modeling. Well, if you are not so much into the big world of discovery, you are more into the commercial side. But I think it's self-evident. The Google system, how much they have gained from the precise GPS system was based on the relativity theory. So that's what motivates me to do modeling. And I hope with this statement and also the previous speaker that you also got the energy and excitement to explore the modeling. Based on my practice as a modeler, where I have practiced modeling in quantum chemistry, mathematical biology, computational toxicology, of course, GIS system, I feel I would like to summarize that there are 3 pieces of knowledge or skills are needed to perform modeling. The number 1 is your domain knowledge, and that's irreplaceable. No matter you are a biologist, geologist, hydrologist, you have your own domain that accumulated over years to guide you to study an interesting question, to pose a question correctly in the field. That's incredibly valuable. Some of you, I think, expressed the little concern that your expert field may not, give you the leverage in mathematics, but apparently, I would argue the domain knowledge is the most important. But of course, on the other side, you also have to build models. Normally, the models were built on top some mathematical framework, and also nowadays you need the computer to perform some kind of mathematical operations. Now, I'm just going to get into the 2 components in the following slides by citing some interesting and provoking thoughts about the mathematics and the computing part. So let's start with the set theory. Does anybody have anybody heard about set theory, or people are familiar with the set theory already? The concept of a set. A set is just it's just like a bucket of numbers, right? These numbers are unique. These numbers are not ordered, and these numbers are put in there according to certain rules. For example, the numbers, the even numbers form a set. The odd numbers form a set, and etc. And set theory actually was the cornerstone to build the entire enterprise of probability theory and the statistics. And that was actually founded by George Cantor back in the 19th century. But the moment when we celebrate about this great theory, there's also some counter-argument. Bertrand Russell has this so-called Barber Paradox. So he has proposed or has discovered a potential problem with the set theory. Mathematically, just arguing this way, if a particular set is defined in such a way that its element doesn't belong to this set, then this set is not definable. For example, if an element is in the set, that means this set is not a set. But if it's not in the set, that means the set is a set. So the set is not a set, and it's a set is a contradiction. It's a little difficult to see if you follow this way, but there's some very nice analogy. It's very interesting. Let's suppose we know Giuseppe is always a modeler and geographer, and he also has a part-time hobby, which is a barber. And he only shaves to those people who doesn't shave themselves. And then the question becomes, would Giuseppe shave himself? Do I get some reactions from this question?
Just for the record, he's not a barber in real life.
Yeah, it's not very important to be in the real life or not, but that's giving a analogy about the problems. So if the barber shaves himself, then he shouldn't shave himself, because that's against the principle. He only shaves people who doesn't shave himself. But if he doesn't shave himself, then he has to shave himself because he's a barber. Whoever have to shave other people who doesn't shave themselves. So apparently you see here, this sharp argument has poked a hole in the set theory. But history have pointed, it's not only him. It's not only Russell himself has this problem. There's also many other preeminent mathematicians has raised the voice, a different voice. For example, Claude Gödel has so-called discovered this Incompleteness Theorem, which was saying is in a mathematical system, you normally start with axiom, then you have a set of logistics or rules that help you to make a proof. And his argument or his paper is talking about it's not possible that you can have this piece of a system that you can have the complete statement of truth at the same time you can prove them, which is very amazing and fundamentally important. That means mathematically it's not complete. I think the way I talk about it probably is not easy to understand. Let's just get another example to show what it means. As you know, Giuseppe is my friend, but people also know the worst enemy of anybody is also himself. That means Giuseppe is Giuseppe's enemy. That means my friend Giuseppe's enemy should be enemy. So Giuseppe is my enemy. However, Giuseppe's enemy is also the enemy of his own enemy. Then the enemy of enemy is friend. Then Giuseppe is my friend. So Giuseppe is my friend or is my enemy. So as you see here, clearly we have a lot of issues with mathematics. So why do I show all these troubles to you? There are several reasons. Number one, with the incompleteness, it opened opportunities for you to make your own argument, an opportunity for you to make new discoveries. And secondly, many times we have these reviewers, sometimes they dwell on trivial argument. Then with this knowledge, you can turn the frustration around and ask them, oh, actually the whole theory of a probability is incomplete. And that's a bigger argument. Well, I will not go into too much about this mathematical part anymore. It's just like a teaser and appetizer at the beginning. And the real key part for today's talk, I would like to focus on will be computing algorithm and analytics. So computing, we normally talk about several elements, arithmetic, where they had one lecture in the past to talk about presenting floating numbers in the computing system. Of course, algorithms also important, but unfortunately, we won't be able to have time to cover about the algorithms. Also have analytics, and we'll do some analytics actually today. So let's go just review briefly what we discussed last time about this algorithm, the arithmetic. So I hope these slides look familiar to you. In the past, we already explained how the numbers are presented in the computer system in such a way shown in this slide. And with this one, we talk about the system we discussed is using a finite and discrete presentation for a continuous and infinite real-time system, real-life system. But I don't know if you understand me or if I made myself clear when I make such a statement. So let's just try to get an example. So this is a very famous example. It's called Hubert Hotel. It's a toy example. It's talking about infinity. So Hubert has a hotel. It's looking like here with many people already living in a hotel. It has an infinite number of rooms. And one time, all the rooms are occupied. Like you go from beginning to the end, including the first one. Then one day, a new guest arrived. And the emergency that he has to find a room. Then Hubert said, well, that's not a problem. I'll just ask everyone move to the next room. Then the first room will be yours. So I hope you can appreciate the concept of infinity in this simple example. Now, if you want to use Hubert Hotel as an analogy of our computer memory, I want to ask you, would the computer memory function as a Hubert Hotel functions? I think this is a interesting discussion point. I want to pause just for a second to hopefully get some reactions from the audience.
What year are these like?
I'm sorry?
In which year were this Hilbert's Hotel analogy was created? Like for me, that's an interesting thing to understand. Like which year does the concept of infinity came into mathematics?
Well, the infinity, I mean, was there for quite a long time. The concept of infinity, why the years is important. The years is, I think you want to talk about time, right? Yes, it's actually itself was not satisfactory in the very beginning as a mathematical concept by itself, but at least I think with the knowledge of your calculus, I think you already know what infinity actually means. So I'm not sure I'm not sure I can understand you correctly where you're trying to get. The example I want to show here is the capability of Hubert using his system to solve the problem of infinity. But my question is, do you think it's possible to solve the same problem using a computer system? If you think one memory address is as a hotel address, if you just think this is a memory is a Hubert Hotel, is that possible or even not? I think we are hitting at 45 time. So I will just leave this one for here and we come back in the next hour and we can continue our discussion. I think I'll stop here unless there are other questions or argument. I hope somebody will have some
this meeting is being recorded.
Thought about Hubert Hotel. Anybody share with me? Or I can provide some provoked thinking.
Well, I was thinking when you were asking Can you hear me?
Yeah, I can hear you well.
I was thinking when you were asking if we can reach that infinity using a computer, I mean, the answer is yes, right? Using interpolation.
Yeah, okay, well, so, okay, maybe I didn't really like exactly, yeah, let me just rephrase it for one time. So the concept of infinity is such a system that, you know, even though you have this current system being filled, you have always room to add extras into it. Actually, otherwise it's limited. So if you think our computer memory is a existing system, once it's filled, like the Hubert Hotel, it's not possible for us to add extra information to it. So that's the difference I'm trying to get. Of course, it's a little, you know, ambiguous. I understand. I know there are some techniques even today with IEEE agreement. There are some treatment about infinity. But what I want to point out is a fundamental difference in the way how mathematics was constructed and computer was constructed. And that relates to the question with arrows when we build models. So we have arrows from the mathematical part using the pure mathematics, and also arrows from the computation. If somebody else wants to, you know, speak about something, feel free. I like to have an interactive action so that we can, you know, understand where we are. I'm pretty sure I try to convey my message in a way, and I hope I deliver to 100%. I'm pretty sure it's probably 80, 70% for years, but maybe even 40%, hopefully not. All right, so I think that's a fun time for the moment. We have a lot of things to work on. Let me just, you know, continue sharing my screen. If I can.
Can I ask a question about the analogy?
Yeah, please. What do you say?
So with the, can we think of like the computer memory? So I guess returning to the analogy, it would be like if you want to open up a room, you have to push the guy on the end out, right? Is that kind of how the computer memory would work?
Yeah.
Okay.
So yeah, so the thing is, you know, it's a finite system. It's a finite system by design in nature. So I want to use example to say, you know, I kept saying we use a finite discrete system to represent an infinite continuous system. You know, I don't know if it makes sense to you or not. That's why I came up with this idea, just to give you a more tangible sense what it means and what the consequence of that, because that's a consequence we face in our real life in computation. So I'm going to show you quickly an example from a coding perspective, how we appreciate this better. Let me just get this one shared. You see my screen? So we'll talk about this.
Yes, perfect.
Talk about this one. So this is a real code, right? I hope Eric can see it. Now let's just leave the philosophy a little on the side. Let's get into coding. So what I'm doing here, so I say x equals to 1 over n. Now n is one of the integers. I want you to show there's a relationship which is stated as n plus 1 times x minus 1 equal to x. And before I jump into it, I hope you can see mathematically this relationship is correct, right? If anybody has any counter argument, please let me know. If not, I will see there's a 1, 2, 3, 4, 5, 6 lines code. You know, I would like you read the code and you tell me the result and what you think about it. Into the full screen, yeah. I think the code is self-evident, right? I just only 2 loops. Anybody want to just explain what I did with the code? I want some volunteers. How about the outermost loop? What is anybody? Does the code make sense to anybody? Well, anybody has questions about code? Anything unclear about code?
Okay, we are getting a value n that is looping from 1 to 11.
Actually, from 1 to 10, because in Python, range goes to -1. So that's the vertical print, the first column, 1 to 10.
1 to 10. Then
Yeah,
I make
that's,
the 1 over the n that I call
yeah, x.
X. Yeah. So that one is going to be the last column.
That's going to be the last column, yes.
So
And there's also x in.
Is decreasing every step going down.
Well, I think you would say decreasing because you said x equals to n plus 1 times x minus 1. Is that correct? Why do you say it's decreasing?
Yeah, I mean, decreasing, it should become smaller.
Oh, yeah, of course. Yeah, x becomes smaller. That's perfect. Because
But
n becomes bigger.
Negative. 1 over.
Yeah, I mean, that's the interesting part, right? So, okay, let me just help you to go through this code, right? So look at the first line here. I said x equals to 1 over n. So apparently the value of x depends on n. So when n becomes bigger, x can become smaller. That makes sense, as Giuseppe mentioned. And n is integer. So I said n from 1 to 10, that means x goes to 0.1 to 1. That's basically it is. Then I want to show there's a relationship, which n plus 1 times x minus 1 equal to x. Is that relationship like a self-evident to everyone? Does it make sense? The equation.
Yeah, is in the inverse.
Yeah. So if you just factor this out, this should make sense, right? This I mean, if you take apart the one on the left side, you arrive at the right side. It's basically just plug in x equal to 1 minus n, you arrive at x. So that's the only thing I want to show with the code. Okay. So what the code does is I let the n run through these numbers from 1 to 10, just to show under different conditions. And in the beginning, I gave this x equal to 1 over n. That's the initial value. Then I called x in equal x. That's basically I keep this value as they initially provided and don't touch it. Okay. Then I go to the second loop. And what the second loop does. So in the second loop, I have a iteration of 30 times. And in this 30 times, I do nothing but rewrite the equation as shown above, right? So I think all of you have approved the equation. Anybody disagree with the equation?
So I'm a bit confused. You're not using k, so.
Oh, well, I'm not using k, that's correct. But it's just that one just to show I have to run this calculation 30 times.
Okay.
Yeah, so the k was not involved. K doesn't have play. The k only trying to run this x equal to n plus 1 times x minus 1 30 times. Right? So this is the only equation I show upstairs in the very beginning, and I think you all agree mathematically that's what it is. So what happens is over 30 times, I just rewrite the equation, which is mathematically correct. Then what happens is after the 30 loops, I print out n, which is the integer, x in is the initial x value, and the output of x, right? So that's the 3 columns you see here. Now, the first column apparently is just the integer n where you put in. The second column, which is x in, as I talked about before, is the initial value I took in and I kept without touching, without going to the second loop. And the third column is the x that's after the loop. So what's your expectation? What's the, what do you expect is x in and x? What do you think, what's the relationship should be x in and x?
They should be equal, isn't it?
Yes, that's exactly. That's what you want to show, right? You want to show there's a relationship, and this is a correct relationship. The x in should be equal x. But did you observe that?
Just in the first 2 iterations, it's true. Then it starts to do some mistakes or something.
Yeah, well, I agree, but only 2. You also see the 4th row is okay, the 8th row is okay. I think that's more or less about it, right? Anybody want to explain what happened? It's about your thinking access. We have all the knowledges provided in the past class to explain what happened here.
Only the 2 powers are working fine. 2 power 0, 2 power 1.
Wait a second, can you speak a little louder? I didn't catch.
Sorry, only the 2 powers are working fine. 2 power 0, 2 power 1, 2 square, something like that. Can you hear me now?
I can hear you, but not very clearly. Somebody else can help to. I didn't really
I can put it in the chat. I can put it in the chat.
Okay, yeah, I'll try to get in the chat if I, yeah. Please thinking, I think it's very interesting, but this is real calculations. What do you think will happen? Only 2 powers are working. Sharp eyes. Why? Please don't stop there. You are very close. Why? Remember okay, not sure what. Remember how we present the numbers in the computer system, right? We talk about the representation of numbers in system, this floating system. But floating is not only real numbers, integers also represented in the floating system. But that means some numbers, I mean, I don't know what you see me or not. Let me share the screen. Let me just stop sharing for a moment because I think you see this equation already. So that means what? That means there's a conversion, right? So you think you put a real number as mathematically it shows, and you put in a system, and you expect it works like this. At this, Giuseppe already discovered sometimes there's issues about single, double float, but there's also another issue. I mean, so related is how this number presented. Are these numbers presented precisely? As this person, I'm sorry I missed you because you just disappeared. Hamalatha, sorry about my pronunciation. She already noticed some numbers are working. Why those numbers are working? Because those numbers can be presented precisely in the binary system. Why the others not working? The others cannot be presented precisely, and over the iterations, the imprecision carry over. And that's due to machine imprecision. It's not a way to get around, no matter what system you use. The more iteration you get, the bigger error you have. So I hope you can use this example to appreciate the difference between mathematical thinking and computing thinking. All right, so let's get into this precision part. What do I mean by this precision? Okay, start sharing. Back to slide. Machine precision, right? So we showed these numbers, all the numbers in computers, how they are presented. And if you, I mean, I hope this doesn't scare you anyway. If you don't look like this, you just think this one as a scientific notation, like 2.5 to the power 10. But instead of the 10 as the decimal place, you should to the power of something. So that's the easy way to see it. But my point is, this system suggests the numbers presented system is bounded in the bracket in the bottom, which is beta to the exponent and the beta to the exponent plus 1. So I think this is going to be self-evident. Just imagine the one equation above. I hope you can see my cursor here. In the parentheses, the smallest value will be d0, because we normalize it, d0 will become 1. So everything else 0, the d0. That means you got beta to the exponent, right? And the largest value will be d0 with everything else filled, that is 1 dot blah, 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 and not to 2, because you use binary system. So actually this number cannot be reached. It's going to be upper bound. So I hope this one is making sense. Now, if you take this one, then you ask about questions about relative error. So what is relative error? Well, the relative error is about how much imprecision you may have if you use a computer to represent a real number, right? That's pretty much beta over 2 times beta minus p. So why is that? Well, beta minus p is pretty much here. It's the smallest digit in the system you can get. And beta over 2, why is that? Anybody? It's due to rounding, right? So it's always 0.5 scenario. It's above 0.5, below 0.5. You're always rounding. So that's a rounding error. Then if you plug in this, you get this new bound. You just rewrite it. You got a machine precision. So what does the machine precision means? That means the error of a scientific number you represent in the computer system is bounded by this one. Of course, there are some numbers are presented precisely, I've seen before, but all the other numbers may bear errors, and this error can be 0, but the largest one will be this one. Why significant? Because this error will propagate. It's not only at the representation level, it's also at the operation level. So what do I mean by operation? So the operation means simply, in this case, it's any elementary arithmetic operations, plus, minus, multiply, division. So that's we always use all the time. Now let's just walk you through what I'm going to say here. FL denote the floating representation. Okay, I hope by this point you feel comfortable when I write X and Y, it's just X and Y in their mathematical sense. But if I put FL, that means this number are represented in the computer system. And OP is operation, whatever you want to plug in here, multiplication, minus, plus, whatever. So what is this equation saying is, when you do an operation on the mathematical numbers, which is X and Y, that's connected by OP, then you represent this outcome in the computer system, which is float, you get some error. And this error equals to the original operation on the real numbers plus a bound, which is 1 plus delta. And this bound is smaller than the machine precision. Did I make this clear to everyone? Any questions? Okay, so all this clear. Let's just see an example. So this is a very simple example. In many times we use two numbers, y and z, addition times another number. So if I want to ask you what the error due to these operations, as we did before in example, when we did calculations, a lot of manipulation and addition. And through this mathematical derivation, you can see the overall propagation is already can be up to 2 machine precision. Now that's why you can imagine if you keep iterating, this number can accumulate and become big and become ridiculous big. So for example, here, I will show you when you have just a simple addition, nothing else. I add two numbers, one is 3.14, the other is 3.14 to the power minus 5. Then I got the result here. Anybody give it attempt? Why? What happened? Do you expect the result? Is it making sense to you?
It seems like the last 3 value, it's not supposed to be there. No?
It's coming from nowhere, right? Why is the last 3 over there? Yeah, absolutely. You have got it. Yeah. Why is this last 3 over there? What do you think? We didn't explain everything.
Yeah.
I'm sorry?
That would be the machine error.
Yeah, it's coming from a machine error, right? As we see before, what is numbers presented this way? 3.4 and 3.14 and 3.14 times 10 to the power minus 5 have different number of digits, right? So if you put this one on the paper, you can see easily one is 10 to the power 0, the other one 10 to the minus 5. That means these two numbers, when you present them mathematically precisely, they have different number of precisions. But in computer, in order to carry out addition, you cannot have these numbers have different different length. It's not possible. You have to shift. You have to shift one to align with another. And as a consequence of shift, you may cut off some significant numbers. You may incur some extra imprecise representation. So that's where the 3 come from. I think you already getting very advanced in this material. And I'm going to throw one more challenge, which is quite interesting and it's very important. It has name also. It's called Catastrophic Cancellation. So what it means when you do a addition, subtraction, you may face significant errors. And this is due to not so much from shifting, but due to the fact that when these two numbers are close enough, due to the imprecision that associate with each of them, you may expect the subtraction become totally 0, but actually they bear a small error, like this 3 here, or even more. And as a consequence, they may propagate. So now I'm showing you another example to see and appreciate this catastrophic cancellation. So I'm have to trying to go through this example with you because it's a little involved, but I would also ask you to depuzzle this by yourself in the end. Okay, so I import a math function here. Import math is just a standard Python library. Then I define a function. This function, I say, okay, I have x, whatever it is. It's just input number. Then I give an order. Order is basically, I want to approximate this number using Taylor expansion, which is a higher order expansion. So what I do here is basically it tells you, okay, it goes through a loop. order from 1 initially is fourth order, then until the end of order. And I approximate this number using this particular mathematical expression. And this mathematical expression is it's precise, as we already illustrated before. I mean, not the same relationship, but it's also mathematically correct relationship. Then I return this particular number, right? So then I calculate, all right, if I put this x is -4 onto order 10, I calculate the result like this. Or if I use the math library, which is directly to calculate this relationship, I got something else. So why there's a discrepancy? Okay, so just I think with the sake of time, it's a little not so obvious. There's a cancellation in the process here. So due to the accumulation cancellation, you see the numbers, the result can change drastically. And that's why we have to be very careful when we perform subtractions, especially which is very useful when we calculate residuals. We use modeling and we use residual to assess the model performance in many instances. Now, if I put a simple example as in a linear system to calculate the residuals, and I want to ask how much error may derive from the pure computational perspective, not mathematical perspective. Well, you can ask this question by laying out this relationship. So I have this linear system with ax equals b, which b is your response variable, x is the explorator variable, a are just the coefficient, and residual is pretty much the difference between your response and your estimate. The estimate is coming from your computational modeling, which I use the x hat to represent. Now, I don't ask about this residual by itself, but I show you here due to the computer floating representation, this system bears error with this data associated with the machine precision, right? If you follow this whole derivation here, you can see the final outcome of your calculation, which is you think is the residual, b minus ax hat, as you always do in your assessment models. Actually, it's not only the residual itself, it's actually residual r in the end times theta delta 2 minus another term. So the residual itself, you calculate it from your system. It's not necessarily just the residual. It's a mixed error propagation from your computation and plus the residual of your system. I hope I made it clear.
Yeah, I think it's clear. And so our aim in modeling is to try to get closer to the machine residual, because better than machine residual, we cannot do it. Or at least if we have a residual, can we split? Can we differentiate between the error of the modeling, so our predictors are not well enough describing the response variable, and the error machine? Can we distinguish these two?
Yeah, great question, Giuseppe. Actually, I'm glad you asked about this one. I think I will address this one in the later part, which is right here. I don't know why I went so far away. Okay, that's about conditioning. So what Giuseppe asked is, we have to calculate residual anyways. That's what we do in practice. And I think I already explained to you, when you calculate residual, you think it is pure mathematical residual. It's not. There's a machine precision always in there. But the point is, this model, the machine precision and the associated error has several components of error in it. So I will get into it. Just give me a little time to lay out this conditioning topic step by step. Okay. So the first one is about question. What kind of question we can ask? Normally, we hope we will ask a well-posed question. So what is a well-posed question? Well, a well-posed question is a question that if its solution exists, unique, and the solution depends continuously on input data. Well, I think that's quite a lot to ask, isn't it? But at least that's the definition from modeling perspective, what kind of question you can ask and you should ask. But in reality, sometimes not all these conditions are satisfied. We remain doing modeling in certain ways, and that's the area we should be extremely careful with the way we build our models and analyze our models. And that basically leads to two questions. One is about algorithm, which we don't talk about in our class. We don't have actually enough time, but it's very important because that also relates to the residual and the final performance of your model. So what that means is basically your algorithm should not introduce actual instability of your solution. So what is it basically, at high level, modeling means? Modeling basically means you want to find a solution. So you have a data, right? You can imagine that there's a data is a territory with a lot of data points, and each of them has some uncertainty. And then you find a solution. And the solution is another space where you have predicted outcomes, and of course, each of them with some associated uncertainty. So what algorithm does is just making a projection, a map from your input data space into your output data space. And this particular projection itself should be nice and clean. It shouldn't be introduce extra instability to your outcome. In other words, it should not cause bigger errors or amplify errors in the mathematical and computational process. If it does, that means your data model is not stable, even though you may observe a one-time small residual, but it's unstable. Unfortunately, we won't cover it, but at least just keep in mind there's another component in there. It's an algorithm. We want to talk about is our solution. So we want to ask that question for all our models, that the solution should be at least well-conditioned. So what do you mean well-conditioned? Well, before we get into the conditions, let's talk about errors. As Giuseppe already alluded to, there are errors from different sources. If I say the total error you can get out of the model is on the left side of the equation, and I can represent this one and break down into two major sources. That's what Giuseppe said, whether we can differentiate the different errors. Okay, so just several notes here. X is your data input. F is the algorithm, which is an exact algorithm, the precise algorithm. And that those X hat and the F hat represent approximation. So the X hat could be, you collect data, there are some errors inside and uncertainty inside. F hat means your algorithm may have some uncertainty or computation. When you convert the data, as we did before, from a real system into a computer system, you carry on some error. Now, if you rewrite the very top expression and break up into two components, you can see this total error can be viewed as a summation of two errors. One is computation, the other one is data. The computation part, we already more or less covered already in the two examples we have done together. And then we'll talk about data errors and how do we treat it. So there are basically two kinds of data errors. One is called a forward error. The other one is called a backward error. So the forward error says it's the difference between the estimate outcome, which is y hat, and difference between the y hat and y. Y is the precise prediction outcome with true value, and many times we may not know. And the y hat is your prediction. Many times this forward error is difficult because we don't know the truth. I think somebody asked the question last time, when we build a geo model, we want to make prediction in places where there are no data. It's hard. It's hard to analyze the forward error. And backward error is kind of another way around. Is a difference between the estimate input versus the true input, and the condition that when you put it in estimate input, you arrive at this estimate output. So in other words, if sometime we cannot find a solution that we really know, this solution can be judged based on the knowledge of truth, because we don't know the truth. But at least we should feel happy if this solution find the solution in a place that the output is in the vicinity of your problem space. So in other words, if your input model data has certain level of uncertainty, given whatever it is, it could be 1%, could be 5%, could be 100%, but that's the data you have. And somehow you generate prediction and output also bounded on a similar scale. And that should be the data you can say that's a reasonable model, that's what you can do. So in this example, I show basically the concept of forward and backward error using a simple toy, which is cosine theta. Cosine theta, as we know, is a precise mathematical function, but we can approximate using Taylor expansion, as shown here. Now, here the approximate algorithm I use is the truncated Taylor expansion, because Taylor expansion, if you take infinite terms, we're going to be precise. So we only take the first terms to approximate. That's where you get the y hat. So in this example, I show if I calculate the precise cosine value when x is 1, is shown here, the corresponding true y value is 0.5403. Then the approximated using the expression shown here is 0.5. Then I can calculate the difference between the two. It's about the order of 0.0403. Now I want to factor back about this backward error, plugging in this approximated solution versus the true solution, it comes out about 0.472. If you look at these two numbers, they are comparable in terms of the magnitude, but the sign doesn't really matter so much. So this example saying this solution you generated is fairly reasonable. Does anybody have questions on this? Did I make it clear?
Yeah, Longzhu, one question. Okay, in this
Yes.
case, we have the, you know, the sine and the arcosine that are the opposite of cosine, and arcosine is the inverse. So
Yes.
with that one, we can calculate the backward. Okay, with the cosine, we calculate the forward error, the arcosine, the backward error. But
Yeah.
do we really have every time also in normal modeling, I mean, in our modeling, the inverse function to that correspond to the arcosine to calculate the backward error?
Yeah, great question, great question. So, okay, first of all, I say in real life, many times things are complicated and difficult. Many times we don't have. And I present this example just as an illustration because it's simple to give you a tangible concept on all these terms I showed in previous slide. But the point here is it's not only the arc cosine, also sometimes the y value is unknown. So I'm going to explain in the later slides what we do in real life to overcome these conditions, including this reverse function and the approximation of true values. But we are in the class, so I only show the very simple examples. The point is, again, trying to inspire your innovative thinking to treat your own problems, because each problem is forward and backward arrow ties to the model part. How do you construct a model? What's the structured model? The linear model is different from nonlinear model. Random forest is different from neural network. So they are all different kinds. But at least this one gave you a basic grasp. And it's simple enough for you to get a good understanding of the concept. Then you can gradually build your own solutions on your own. Okay, just follow on. As I mentioned before.
Question?
Yeah, please.
So is there an acceptable amount of error, that you would consider? So I come from like a physiology background, and our statistics is like looking at p-values and looking at anything greater than 0.05 would be not statistically significant. So when you're looking at an error in your model, at what point do you say, okay, this isn't gonna work?
Yeah, I heard you clearly. It's a great question. I knew you're not only you, and also in other statistical modeling, they look at p-values, they look at a particular significant levels, and to call, okay, this is a cutoff. But I would say, even with p-values, you have to claim at a certain level of confidence, this is okay. And in terms of the condition numbers, we do have a relationship, and we hope this condition number should be close to 1. So the closer to be 1, the better you are in a model position. Now, it become a little arguable if it's become 2, 3, 5, and that has to be case-by-case study, and your expertise has to kick in to help you analyze. Maybe in your practice, the field you are in, the data are inherently noisy. It's too much to ask to get this very pure outcome. If you are from physics, where I used to study, we look at the 29 decimal places. So that's a different question. So it's a great question, but I think the answer varies depending on the field. So let me just finish this slide, then we can go to another break. This one is quite important. That's pretty much a follow-up of this one we discussed before from forward backward arrows. And you can see the conditional number, it's pretty much defined as the ratio of the forward arrow or backward arrow. I mean, more precisely, the relative forward arrow divided by relative backward arrow. And this one can be approximated using the equation on the right-hand side. You see here, using this approximation, you got rid of this y already. Now, I think we are coming to the point for break. I will leave you, if you have interest, to derive this relationship on the right-hand side. And also I pose a question. So this is a conditional number for the function f. How about the inverse function? What's the conditional number for the inverse function? So with that, I will stop here. We come back at the exact hour. I think it's 17 to somebody, or 16, 18, whatever, the exact hour. Thank you. Maybe a little unfamiliar.
This meeting is being recorded.
To many people. In case you have questions or anything, it's good to stop here, because the last leg is the most intensive one. Looks like no questions. Okay, so let me just keep going. Okay. Let's share the screen. Screen sharing. Here you go. I think you can see the screen now. We stop here in the last part, talking about conditional numbers. I also give you a question to think about, the inverse function conditional numbers. I hope somebody can have interest on this, then we can talk about it next class. If nobody has interest, then we just let it go. Doesn't really matter so much. Okay, now this part, we'll focus on calculating the conditional numbers for the linear system. The reason I chose the linear system is it has a closed solution. Is easier to assess. It doesn't mean that for the nonlinear system it's not possible. It's just a little more complicated. So I think in the beginning, I just want to lay out this good foundation. We use a clear and nice system to calculate, understand the behavior of conditional numbers and how to calculate it under different conditions. Actually, I have two examples here. One is a linear system. The other one is overestimated least square system. So when I say linear system, I mean specifically is a system of linear equations. Back to days when you study linear algebra, it's pretty much write down a matrix, operate on a vector, you arrive at another vector. So it's a system of linear equations. That's what I mean by a linear system. Exactly, I'm showing here. So the conditional number for this system has been worked out is pretty much equal to the mode of matrix times its inverse. I think the matrix inverse is not a, I'm sorry, the matrix inverse mode is not a problem. And the matrix mode may be something not familiar with. So I prepare one slide to further explain what is matrix mode. It's called actually matrix norm. It's defined as such as a ratio between the matrix times a vector and divided by vector. And this vector actually is called inducing vector. And this is one way to define matrix norm. There are multiple ways. Right, I hope vector norm is something people feel comfortable with. In case not, I just remind you, there are three commonly used vector norms. One is L1 norm, the other one is L2, the other L3. And the definition are listed here. So the L1 norm is nothing else but the absolute value, the summation of absolute values. And L2 norm, it's pretty much you're familiar with, it's a Euclidean distance. And the infinite norm, it's a little, probably not many people have encountered before, is a maximum value of a system. Now, given the fact that I have shown different ways to calculate norms, then you may wonder, what's the difference? What's their relationship? Before I go on further, I was wondering whether anybody may have the answer already, who are already familiar with the concept of vector norms. No one? Okay, well, that's not a problem. But we know what vectors are, right? Everybody knows what is a vector. Vector is a quantity and the direction. So let's work out the example shown here, which I draw some circles and squares, and I put their coordinates, and I labeled a particular point P. And if I present this P point as a vector, and the corresponding vector elements is nothing else but it's a coordinate on this graph. So what's the coordinate of P? It's 0.5 on the X and 0.5 on the Y, right? All right, I hope we are happy with this. So P is 0.5, 0.5. I ask you to calculate the X1, X2, and X definitive norm for this value. Let's do it together. If I quit the entire screen, do I see other people? I don't. It's a little bit challenging now. I'll go back to the screen. It's easy. You don't even need a pen or paper. You can just look at the graph and tell me what you get.
Could you repeat the question, please?
Yeah, I want you to calculate the norms, the 1 norm, 2 norm, and infinite norm for this point P.
And for the norm, which is the norm? The vector norm is the red line?
The vector is a red line, right? From 0 to P, this is a vector. And the coordinate of P is 0.5, 0.5, right? Because it's 0.5 on X and 0.5 on Y. So the coordinate is pretty much the vector representation of P. P is 0.5, 0.5. Now, given this one, I'll ask you to calculate the 1 norm, 2 norm, and infinite norm for this P value.
Infinity should be 0.5.
Sorry, infinity should be what?
0.5. Sorry,
yes, correct. You got it. Score. Okay, how about 1 norm?
I chose the simplest one.
Yeah. Okay, that's a good start. Somebody else. Try with the others.
So now we need to calculate the blue one.
No, calculate the 1, 2 norm. Same point, P.
Yeah, can you identify the 1 and the 2 on the graph?
Well, it's a number, right? So P is a vector. As somebody already voiced, P is pretty much X here. So I use P to represent a vector. It's go from the origin to this point. And its value is 0.5, 0.5. That means the 2 components of P is 0.5. That's why somebody voiced out the maximum value is 0.5. That's why you got the infinity. Then for the 1 and 2 norm, you basically just plug in this equation, right?
So for the second one, it should be also 0.5, right?
The 2 norm, no. Why is it also 0.5?
Ah, no.
Because they have a look, they're a square, and they're also
isn't
the square root.
No, you're right.
So the norm 1 is just the sum of the 2 components?
Yeah, the first one is just 1. It's 0.5 plus 0.5.
And the other one is square root of 0.5.
Yes, okay. So I think you all got it. And I think through this access, I gave you a sense the relative difference among these three different kind of norms, and they actually have a rough relationship. Normally, they are pointing the same direction. So that means if one norm is big, two norm is also big, infinite norm also big. But the exact number for each norm may vary depending on the conditions. But this is a simple graph and easy enough to help you to see which one is generally bigger than another. Normally, one norm is the biggest. All right. So I think I just want to spend one more second to make you feel comfortable, because we need to talk about norms. So from vector norm, you can get into matrix norm. From matrix norm, you get into condition number. So that's why the norm is important. Okay. Now, so far, what I talk about is a very simple case. This is a 2D graph. Then things get complicated when we move to a higher dimension. Now, this graph is basically a histogram I show of the distance of two random points sampling on 100,000 times. And the result are in different dimensions. It starts from dimension 3 all the way to dimension 100. Once again, this is a histogram. I just pick two random points in 3 dimension, 10 dimension, 100 dimensions. Then I calculate the distance, the Euclidean distance. In other words, the L2 norm. And then I plot this distance on this graph. Then I see this thing, whatever is shown on the screen. I want to ask you, do you see some difference? Do you see some pattern? Do you see some features? And how and why? Did I make my question clear?
Yeah, I think you need to repeat the graph and the dimension problem.
Yeah, I don't understand the 3, 10, 100. What's the distinction there? That'll help explain the question.
Yeah. So the 3, 10, and 100 are dimensions. So 3 means 3 dimension. 10 means 10 dimension. 100 means 100 dimension. Okay, let's take a 3 dimension like example. Okay, I create a 3 dimension that's in the same here, which is a unit, unit circle. But it's a 2 dimension. I make a 3 dimension still in the unit circle. Then I just pick 2 points, random points from this circle. This 2 dimension. I put random 2 points. Then I calculate their distance. That's 1 time, 2 times. I do 100,000 times. Then I got 100,000 distance. Then I plot a histogram of all these distances, and that's how I see for the 3 dimension. I do the same for the 10th dimension, which is also a histogram, and look like such. Then again, I do 100 dimension. I also plot a histogram, and I see another histogram. They look all more or less normal shape, but they become thinner and thinner, right? Do you agree with me? If you look at the shape of this histogram, it's becoming thinner and thinner. Is that correct?
I agree. I do not know why.
Yeah. So I mean, I just by looking at this, it's becoming thinner and thinner. So what that means?
Well, the variation is smaller, I guess, with the increased number of dimensions.
Exactly. That's the point. So very good. In 3 dimensions, you can imagine the total space of small dimension is apparently smaller than 10 dimension or 100 dimensions, right? But if I draw 2 points, I have likelihood to occupy almost everywhere. You see this goes from 0 all the way to the upper bound. Now, if I move to 10 dimension, I see my 2 points are getting more close to somewhere in the middle. But if there, the points are really far apart, I don't really observe so much. And the observation become more dramatic when you go to 100 dimensions. That means when you increase dimensions, the distance between two random points getting closer and closer. The variation becomes smaller and smaller. Or in other words, they become less and less distinguishable. And that's a problem. Why is a problem? Because in many ways, we model high-dimensional phenomena, no matter it's experimental variable or many other observations. We want to ask the question, how good the model is, how different one versus another. Then when you compare these quantities in higher dimensions, which metric you use? So we use Euclidean distance many times, but you see here, when you go to higher dimension, you see everything getting closer. It doesn't really tell you much in terms of difference as you would like to. I hope this observation doesn't disturb you. It's a known phenomenon in modeling. It's actually called the curse of dimensionality. I just want to see a simple example to illustrate the concept and hope you can bear it in the back of your head when you start analyzing and modeling. It's not something we can tackle right now because we still want to go with the simple examples. But this is example I will show here because it's relevant. It's a L2 norm. It's widely used and many times incorrectly used. All right, so let's get into our linear system.
Sorry,
so
Longzhu,
linear system.
One point to this point, to this previous graph. Would that mean also that increasing the dimension of, because the dimension are nothing else that the number of predictors that we have in our modeling?
Yeah, you can go in this way, yes.
Yeah, so increasing the number of predicting reduce our ability to distinguish the error, a potential error.
To distinguish the difference.
Yeah, between predicted.
Between one variable with another, yes.
Okay.
Because they come all together, they look all the same, or I mean, not exact same, but very close, very similar.
Okay, yeah, good point. Thanks.
Can that basically relate to saying that as you increase the number of variables, it becomes more difficult to discern the importance of any one variable compared to others?
Yeah, that's a valid statement. And also you can state, many times you want to compare, I want to say, okay, I have one point, a particular observation, and that has been described by my multi-dimensional explorated variables. Then I have another observation. So I want to say how close they are. For example, you want to use the nearest neighbor for clustering, right? In the nearest neighbor algorithm, one important question to ask is the distance between 2 points. And these 2 points distance is described using the explorative variables. And these variables are higher dimension. Now, if you want to compare the distance, you compare the distance in higher dimension. That means they are all similar. I think that's more or less I get. Yeah.
Sorry, Longzhu, one question. So in a system where you have more dimensions, the magnitude of the error becomes, it's the magnitude of the error is relative then, and you have to account for the magnitude of the error to be able to determine the error from the observed point. But the magnitude starts to carry significance. So you got to set the threshold for the magnitude differently, right?
Yeah, I think the magnitude we know as the dimension increase, the space expand, right? It's getting bigger and bigger.
Yeah, I'm just going back to the point JD raised earlier regarding magnitude. How do we know then what is the right magnitude, and what is the right, what is the appropriate p-value?
Okay. Yeah, I think we are guiding. I mean, this is a very good question. But it is also $1 million question. I don't think there's a definite answer, but answer really depends on your exact case. you have to really, I mean, we can really actually spend some time in the future lectures to talk about the dimensional issues. I didn't really want to go into so much in that because I talk about this norms. That's why I want to bring this to your attention. The use of this metric for measure of distance in the higher dimension demands extra care.
Okay, thanks. It was a genuine question. I didn't want to put you on the spot. I just wanted to know if there was a solution around it, but that's fine. We'll cover it later.
I mean, yeah, there's I mean, okay, there's not so-called solution. There's a way to diminish this phenomenon. For example, if you work in the 5 dimension, the solution may be different from you work with 25 dimension. So it really depends. Now, one thing you can do is you can use different metrics. I show here. I show like 1, 2, 3 infinity norms, but this norm actually goes to continuously. You can have 1.5 norm, 1.2 norm, 2.5 norm, but they all come out to give you different numbers, as I shown here. When you have different norms, you get the numbers, and you translate into different behavior in the high dimensions. So one thing you can do, you can try, or you can analyze from a theoretical perspective to see which one is the most appropriate based on your data. I hope that answered it
yes,
better.
Thank you. Yeah.
All right.
Yeah,
one more.
Yeah, I have a question. Like, distance between 2 points is like one will be the model and the other will be the phenomena we're trying to represent. So the distance is like the accuracy. That for me, it's a bit.
Okay.
I didn't understand it.
Okay, that's one way to interpret distance, but the distance could also be the 2 observations, right? You have 2 observations, you collect it, then you ask the model to make a classification or clustering. You ask how, let's say you collected 100 points. You want to cluster them into 2 groups. And where's the division line, right? To calculate distance between these 2, among these 100 points, you have to find some descriptive variables. I don't know, you may get from rainfall, from elevation, from vegetation, from whatever you collected. You got a higher dimension. I don't know how many variables you have. Maybe you have 50 variables, maybe you have 25 variables to describe or associate each point. Then the distance between this point will be represented by the distance among these higher dimensional vectors. And that's where the challenge comes from, because when you move to higher dimension, the distance diminished. So the space is getting bigger and bigger, and they're getting closer and closer. The points.
Okay.
All right. Did I get that more or less?
Yeah. Thank you.
All right. You're welcome. Okay, so let's get into our linear model business. So this is pretty much the way we represent a linear system, as I did before. It's a linear system, linear equations. We are interested in residuals, as we always do. Once again, the head is the estimate or the solution coming out of our linear model. We calculate difference between this B is your observe, your response variable, or the data you collect in the field. Then you have this A, which is a matrix containing all the columns you created from landscape, from rainfall, from vegetation, everything. Then you estimate this particular coefficient. Then you hope the residual to be 0. That's going to be 100% accurate, make a prediction, but sometimes not. But the point I want to drive to you is through the derivation. If you are interested in, I encourage you to go through the derivations, then you can understand. But I think for the sake of time, we don't get so much. I want to just get you to the final point. Okay, the final point is our interest is this one. In our case, in the linear system, the delta x is actually our interest. It's the solution of your linear system, which are also the coefficient of the linear equations you resolve. And you see this arrow is bounded by these things on the right-hand side, which is a multiplication of conditional number times residual divided by the matrix norm and vector norm. So the matrix norm, vector norm, whatever it is, we cannot do much. But the key point is this arrow is not only reflected in the residual, it's also reflected in the conditional number. If you get a situation that you got a small residual, but you got big conditional number, your arrow bound is also not good. Your model is still not a good model. So this is a key point I want to demonstrate for this linear system. Now we go to linear square. Least square, with a more general system. So the difference between least square and the linear system is, I hope, is self-evident. The linear system is exact. The number of equations is equal to the number of coefficients you want to estimate. The least square is overestimated. That means many times you have more observations than the variables you want to, than the parameters you want to estimate. And that's normally the case we deal with when we build GIS models. That means you have more rows than columns. Then what do? We do an optimization. So like before, instead we can get a solution exactly out of your linear system, then you have to do an optimization, which you select the target function, you do some optimizations, then you equate the first derivative of this function to be 0 according to the theory of calculus, so that you can get a minimum. Well, I'm actually a little cheating here. It doesn't guarantee its minimum. It could be minimum or maximum, but you can actually analyze the situation because it's a convex system you secured, and you can also you secure you have there's a optimal solution, and also you can assess the second derivative to ensure yourself it's a minimum. This part will we had a lecture before to talk about optimizations, but here we're just trying to get the key point. The key point is the normal equation, which is looking like this. So this is pretty much equation that after all these optimizations you want to use to derive a solution for the least square system. Maybe it's a little too messy, so I prepare something more graphical for the actually more graph-oriented audience. So once again, the same system. Look here, I change the notation. So B is your original, which we talked before, the same B here, but introduce another term is Y, which we don't really use or observe, but this is a relationship. So this is your observations you got from the field, variables, and R is a residual. We talk about residual, right? This is difference between B and A times X. Then this is Y. So the Y is a hidden determined vector based on your exact system, and there's an angle between your actual observation and the exact system, and the angle is pretty much corresponding to the residual. So the smaller residual is, the closer is between the observation and your underlying true system, and the better model is. So in other words, the smaller the residual, this B is moving more and more closer to this one on the this plane is called span A, closer to span A, and this theta getting smaller and smaller, and that your model getting better and better. So in order to do this, you can show a projection. So I'm showing here, it's pretty much a projection, right? I have a vector here, I make projection on this plane. And to construct this one, we have to introduce the concept of a projector matrix. So this matrix has some amazing properties. The most interesting ones are the repeated projection is still itself. If it's orthogonal, the transform is equal to self. And if this one is orthogonal, you can also define a perpendicular projection, which is pretty much identity matrix minus this projection matrix. And you can also divide the space into two components, which is projection by itself and the complementary projection or perpendicular projection of the same vector. So in other words, if you have an orthogonal projector matrix, you can carve this vector into two parts, and each of them will be used to project this vector into the corresponding complementary perpendicular space. And if you carry on this notation into our system, as we did before, you arrive at this equation. And this equation is kind of important, not for the fact it's projector axis, projector matrix, but for the interest to figure out what is the projector matrix. So if you compare this equation with what we did with the normal equation as shown here, I hope you can believe me for now, but I hope you can carry out calculations by yourself. You can show this is how the projector matrix look like. So what it is, it's pretty much a bunch of combinations of your design matrix, height matrix. I think, depending on you from economy, from statistics, you have different names, but this is how it looks like. So now it's time for question. Can you show this matrix I'm showing here is indeed a projection matrix? Can this projection matrix be an identity matrix? I know I'm a little fast here, but I'm just curious. Does anybody want to respond right now on these two questions? Going once, going twice. Okay, no problem. I leave this one as a thinking question on your own, and hopefully we can get some interesting response next time. All right, so now let's get to the least square system conditional number. Actually, the question here relates to this construct of conditional number. We cannot calculate the conditional number of the least square system as we did with a linear system. The reason is, if you understand this, you understand why. So I will not just disclose at the moment. I'll leave it to you for a moment to think, but I tell you the solution here. So in the least square system, we have to construct a so-called pseudo-inverse matrix, which is denoted as A plus. It's a combination of several things. Then the conditional number of this least square system is actually a multiplication of the matrix norm and the pseudo-inverse matrix norm. And once again, I want to illustrate one more time about these residual calculations. So this is about the least square system. I introduced a perturbation to the system because our observations bears errors. If you don't really care so much about derivations, but I encourage you to try to look at this. It's quite interesting. Actually, there's one fundamental property I didn't introduce, but if you care enough to go through this one, you'll find out, and we can discuss next time. There's only one thing missing, but you can, if you find out, and we can talk about it. If you don't really care so much, yeah, we don't really worry. So the solution, the conclusion, right? So the conclusion of the system, once again, is the arrow bound of our interest, because X is our solution, is bounded by the conditional number for the least square system divided by cosine theta. What's the cosine theta? Remember we talked about cosine theta before? It's here, right? The smaller the residual, the smaller the theta. Okay. So we see once more the arrow and the solution of your linear least square system is conditional on several terms. Conditional number and the cosine theta, which is related to the residual. So the residual only tells you something. Let's say residual is small, then you want to claim your model is good if your conditional number is good. So that's the conclusion. Now let's go into a real example so that we can, don't look at this formula so much, look at numbers. let's say you have the numbers for here. I show in 2 columns. The one on the left is x. The one on the right is y. I want you to fit a curve, polynomial. We talk about polynomial so much on Tuesday. So let's continue fit a polynomial curve and ask you specifically to fit the 4th order. All right. So what that means? Anybody remember? Should I bring the slides last time? We have a polynomial interpolation. So it's not interpolation, it's fitting, but it's very similar, but the same concept. So you create a matrix, which goes to the power of your whatever you want to raise up to, and you create this matrix, and you try to do a fitting. Instead of interpolation, which is analogy of a linear system, you do a fitting, which is a least square system, okay? So this is the matrix you got. So you calculate from the above, you get this matrix, then you fit the curve. That's the numbers I took from there. You look at this one. So somebody want to comment, what do you think? This is fitting is good or not? Reasonable? Not reasonable?
Right, okay.
Sorry?
Very good.
Yeah, looks not too bad, right? When I look at it, it looks not too bad. Looks not too bad. Yeah? So how do we assess? We look at the conditional number and we look at the cosine theta. As the cosine theta is quite small, that's your residual. In other words, it's quite close to be aligned. This projection is pretty much lie down on the span of your plane. But look at the conditional numbers. What it means?
Sorry, Longzhu, once again, how you calculate the condition number?
So the condition number is this one. It's a least square system. So look at the conditional number. What this means? This means, okay, you got lucky this time, but the system is super unreliable. All right, I think I'm writing close to the end here. Just want to take home message. The conditional number is very important. I have actually one reading assignment for everyone. This is a paper written by hydrologists in the field of geodomain. They discuss some important questions in geoscience. I hope you can read it and steer some discussions. Actually, I'd be happy to hear some words from you next time if you have interest. But if none of you have interest, we can just drop it anyway. Yeah, that's all I want to talk about. I will stop here. I'll leave some time for questions in case there are any.
What was the name? What, can you repeat the name of the article, please?
It's on the slides. You can download it and you can just Google it. It's everywhere.
Okay.
Yeah, Longzhu, can we always calculate the condition number?
Well, that's a good question. So there's always human brain to crack difficult problems, right? So the reason I present today is those condition numbers have the closed form. We can have the analytical mathematics to help us to analyze. But there are other difficult cases. We may have to use a numerical strategy to get this conditional number. But this number should exist. Maybe it's not exist in a closed form, but we can estimate. We can always estimate. Thanks for posting this article.
We always talking about residuals, but the residuals, they are bounded or they are related to this conditional number. So
okay, the point is, the key question you want to ask after you getting a model is how good your solution is. Now, many times we understand the quality of our solution only through the concept of residuals. But what I want to illustrate in our system, the simple least square and linear system, to show that it's only true if your conditional number is small. And I will also demonstrate some instances that you may have a small residual, but you have a huge conditional number. And that means your model is also of value if you use it, especially you use it in the area you don't know.
Okay, thanks.
I think I went through a lot of derivation today, and some part, pay attention. If anybody has interest to go through, I may have some typos because I realized when I saw it, but no problem. If you have interest, please go through. The conclusion should be correct. I noticed some typos, I will update on my side. But if you do notice something and you go through by yourself, you detect the errors, feel free to make corrections or questions that we can discuss next time. And there's a famous physicist, I think it's Fermi. He was very well known, and so Nobel laureate, and his lecture notes were known to be full of errors. And his students become so good because they spend most of the time, instead of following lectures, they're correcting errors. Then they understand the system by themselves. So I'm not trying to set up for myself as an example, but at least go through the derivations does help you, at least in the mathematical terms. You know, when I read a book, the geophysics book or mathematical books, I do go through the derivations by myself as much as I can. Some of them may not so clear, but at least the one I present today, I consider they're durable if you want to make a mind to go through everything. Yeah, so actually somebody asked me about the interpolation from last time. I don't know who still have questions. I just bring up the slides once more in case anybody have question or something, because I think we have 2-3 minutes in case. I think there's some question about this sublime. Somebody may have questions. I can share the screen once more. Yeah, I realized yesterday the lecture was a little intense, actually more intense than today, because we mostly covered the linear system. So this is pretty much, you know, the polynomial fitting. This is kind of relevant to today's lecture. I wasn't sure which part exactly wasn't clear yesterday. If somebody may have questions, feel free to ask. I'm happy to address it. All right.
Okay. Thanks, Longzhu. We will see some application of this theoretical background in our modeling technique to understand, you know, when our model and our residual can be improved or not, because sometimes the residuals are that amount that cannot be included, it cannot be improved anymore because we bounding with some conditional errors that we cannot overpassing due to some mathematical constraints, let's say, or computational constraints or arithmetic constraints, like you mentioned. So it would be nice to see the application of this theoretical part on the following days. Okay, thanks for the lecture.
For my part, yeah, we'll see you next time, I think.